Hello. So far we have discussed numerical solutions of ordinary differential equations. Let us start discussing about partial differential equations. Okay. So, as you could recall, the solution of an ODE will be a curve. Okay. So, it represents a curve. So, before we proceed to numerical solutions of PDE, let us review a bit on the definitions and then classifications, and maybe if possible little bit of theoretical sense. Okay. So, let us start introduction to partial differential equations. इंट्रोडक्शन टू अभी नहीं है ना. So let us, I would like to stick to first order. Okay. First order, and in general any functional relation, for example u x y dou u by dou x. Okay. So, this is called a PDE, where u is dependent variable, x and y are independent variables. Okay. So, however, depending on the form of f, one can classify. Okay. So, for example, let us denote, this is a standard okay. So, this is a standard notation. So, now with respect to the standard notation, so we would like to classify. Okay. Consider the form so this is partial derivative with respect to x, partial derivative with respect to y, so if a PDE first order, of course, because only the first derivatives are involved, if it is in this form, remember that means with respect to u x and u y it is linear. However, the coefficients can be of this form, it can depend on x, y and also u, of course, the right hand side. Okay. So, such a classification is called quasi linear. Okay. So, examples, so I will switch over to P. U x is P Q okay. So, these are examples of quasi linear. Okay. So, now suppose Suppose equation is of this type. So, that means A and B are independent of the dependent variable u. Example, okay. So, this is see right hand side you can have nonlinear term. So, linearity with respect to only the first derivatives. Okay. So, this is semi-linear. For example, if it is of this form, say so, this is linear. Okay. So, this is linear. Further, this is non-linear because we are allowing any combinations. So, for example, okay. So, this is non-linear. So, as I mentioned, suppose you consider something like that. So, what is our notation? Okay. So, what do you mean by solving 1? That means, we would like to obtain okay. So, we would like to obtain a solution of 1. So, then we say we have solved 1. Okay. So, having classified first order PDEs, it would be worth discussing in brief how do we approach the solution. Okay. And first of all, what is the solution? As I mentioned, in case of ordinary differential equations, the solution represents a curve. So, one can guess in case of partial differential equations, since we have one dependent variable and two independent variables. So, definitely as you vary with respect to this, one would expect solution represents a surface. Okay. So, let us try to understand little bit on the solution. Okay. So, let us consider so we can play with the notation as long as we understand. So, I am introducing z. So, this is our dependent variable p q okay. So, this is a quasi linear. Okay. So, z is dependent independent. Okay. So, now let this be the solution of 1. Okay. Suppose this is a solution of 1, right. Now, 1 can be represented as follows. So, these are all functions, right, p, q, where p is, so we can so p, q, r dot p q minus 1 equals to 0. So, it can be put it in this form 1, look at carefully. So, if you bring it minus r, so I have taken p q r there and here small p q and minus 1. So, exactly one can be represented in this form, but remember, suppose this is some z equals to z of x y, this is a surface. Okay. So, then n bar, the normal is z x, z y minus 1. Okay. So, therefore, so but p q minus 1 is normal to the surface z at each point. Okay. So, normal, this is normal to at each point, but what is our relation? Our relation is p q r dotted with. So, this is normal to our surface, and if you call this is a vector v bar. So, we have v dot n 0. So, therefore, what is the inference? Our inference is v bar must be in the tangent plane to the surface, isn't it? Okay. So, suppose this is z equals to f of x y, the surface. So, this is our normal. So, therefore, p q r must be in the tangent plane. So, what is our inference? Hence, p q r must lie in the tangent plane to the surface okay, whose equation is okay, where these are the coordinates along the plane. Okay. So, what is this star forcing? Star is forcing that all the surfaces satisfying star are such that at each point they are tangential to the vector. Okay. So, what is the remark? So, the remark is what is the remark? Star is forcing that all the surfaces satisfying star are such that at each point they are tangential to the vector. Okay. So, which means what is happening here? See, if you can visualize a solution of a PDE as a surface. So, what is happening? The star, what is that relation? The vector v bar, which is consists of the coefficients p, q, r. So, that says that it is along the tangent plane. Okay. And you have a surface like this, and normal is like this. Okay. So, hence the vector p, q, r must lie in the tangent plane. Okay. So, if you take all surfaces containing this p, q, r, okay, so they have this special property. What is that property? They must be coming from star. Okay. That means all these j's must be solutions of that particular PDE. Okay. So, let us visualize this clearly. Okay. So, therefore, these surfaces must be made up of curves that are tangent to p, q, r at each point. Okay. So, these surfaces must be made up of curves that are tangent to p, q, r at each point. That is what I just explained. Okay. So, let this be the parametric form of these curves. Okay. Suppose this is the parametric form of these curves. So, then the tangent vector is given by where S is the parameter arc length. Okay. So, this is the tangent vector. So, now from star, what is our star? P, Q, R, so this is n bar, this is v bar, this is 0. So, we have noticed that v bar is along the tangent plane. So, therefore, our inference is, see, this is the tangent vector. So, therefore, dx dy and dz is parallel to PQR. Okay. So, this implies dx by p dy by q dz by r. So, this represents a system known as characteristic system of our PDE. So, this is known as the characteristic system of PDE. And what will be the solution of this? Yeah, obviously, solution of this will represent, see, if you take these two and solve, you may get one and take these two or take these two. So, depending on that, however, you get, yes, 2 parameter family of curves. So, solution is a 2 parameter family of curves, and these curves are called characteristic curves, because depending on the character of these curves, family of curves, the solution is obtained. Okay. So, let us briefly discuss. So, from this we have arrived V bar is parallel to d x bar. Okay. So, this implies dx by p dy by q dz by r. So, this is a first order ODE system. This implies we get two parameter family of curves which are tangent to V bar at each point. So, these are family of curves which are tangent to PQR each point. Then once we have this, we get a functional relation. You can express a functional relation okay. So, as arbitrary function. Okay. So, let us see how we arrive at the solution. Okay. So, let us take simplest examples to start with. So, z is a dependent variable, x and y are independent, c is a constant. So, now the characteristic equation is dx by c dy by 1 dz by 0. Suppose I solve these two. So, these two implies say y equals to 1 by c x plus c 1 okay. Then suppose these two implies, so other two implies z equals to C 2. Okay. So, we have C 1 equals to right, then the general solution is psi of okay, or otherwise z equals to some function of, we can write okay. So, this is a solution surfaces. Okay. So, this is very standard technique in literature called Lagrange's method of characteristics. Okay. So, let us look at another example. Okay. See, this time let us represent, this is our surface. Okay. How do we form a PDE? So, we would like to form a PDE corresponding which governs this surface, that means solution of whose PDE is the given surface. Okay. So, you differentiate. So, z x is p. So, then f dash with respect to x is 2 x. So, then with respect to y, so this implies p y minus q x is 0. This is our Gaussian equation. Now, let us go back to this. How do we do it? From here, dx by y dy by minus x dz by 0. Okay. So, from these two we get x square plus y square C 1, and from these we get z equals to C 2. So, therefore, the function is which is this one. Okay. So, the characteristics are family of curves. So, in this case, what are these family of curves? Look. So, in this case, if you keep on varying C, suppose C 1, some C 1 0, C 1 1, C 1 2. So, this is for each C you are getting curves. Okay. And you are getting z equal to constant C 2. Okay. So, these are the planes z equal to constant. Okay. So, you get family of curves, and the surface generated by this represents the solution. Okay. So, what we may get something like okay. So, this is the solution of this PDE. Okay. So, we have also discussed how to obtain PDE. Okay. So, we have just given a first order PDE, how do we solve? Of course, quasi linear via Lagrange's method. It is a hard way to do a nonlinear stuff, but we will just have some analytical rigor, and then we proceed further to numerical, which is the aim of the current lectures. Okay. So, sometimes what happens, you find the solution, but subject to some initial data. Okay. So, this is also an interesting as far as first order PDEs are concerned. So, let us briefly discuss. Okay. So, this is called a Cauchy problem. So, Cauchy problem is a x y u, okay, then u x b x y u u y c x y u. So, I am purposefully, it is just for an understanding, it need not be p, it is not based on notation, it is based on our understanding. Okay. Then suppose gamma is a curve, okay, in xy plane, then what is Cauchy data? Cauchy data is prescribing u on gamma, okay, prescribing u on gamma. So, for example, so now u is 1 on x equals to 1, okay. So, this is, so that means in parametric notation, say y 0 of s is s, x 0 of s is 1, u 0 of s is 1. Okay. So, that means we expect not only to get the solution, but the solution which passes through the initial curve. Okay. So, for example, this is a kind of initial condition. So, let us see dx by 1, dy by e power x, du by y. Okay. So, now we can solve two of them. So, any combinations. So, we get okay, then du. So, this is solving these two, then we solve du is y dx. So, this is implies u equals to so total. Okay. So, we can represent some function of c, because we need to eliminate. So, this implies what we get du is y dx. Okay. So, y is this. So, we got this. Okay. So, therefore, u is by eliminating. Okay. So, this is y minus E x into c into x plus f of y minus E x. But our requirement is you must follow this. Okay. So, therefore, u of 0 y. So, this will be 1 plus f of y. This implies f of y is y. So, therefore, u of x y is obtained as okay. So, this is satisfying some initial data. So, this is a typical Cauchy type problem. Okay. All right. So, so far we have it is with respect to first order PDE, okay. But still we have not got exact idea of what are the characteristic curves and then how the solution is related to that. So, let us try to understand with respect to some examples. Okay. So, let us discuss some examples. So, this is first order. It is very elementary because with the constant coefficients. Okay. So, this is of the form what we have started, that is p plus q equals to, though p and q are constant coefficients. So, we can adopt the method. So, using Lagrange's method, okay. So, now from these two we get right. Then let us consider these two. So, these two we got this. So, from these two u equals to C 1 plus half sin x. Okay. So, C 1 equals to f of c will be our solution. So, u is 3 x plus 2 y plus half sin x. So, this is our solution. Okay. So, let us try to understand little bit. Let zeta equals 3 x plus 2 y, eta is, so then the solution becomes u equals to f of zeta plus half sin zeta plus eta by 6. Okay. So, what is the scenario geometrically? You can see suppose this is 1. Okay. So, then we would have okay. Then we have u equals to C 1 plus. So, now for some particular value, okay, so we can get so this is a intersection, this is the background. So, you have two planes intersecting, okay. So, this is a curve where it is getting intersected, okay, and this is integral surface. What is that? The solution surface is called the integral surface. So, these integral surfaces and then these are the planes which we got from the characteristic equation and they intersect along a curve and this curve is called a characteristic curve. Okay. So, if you can recall, so take some irregular cylinder. Okay. Suppose these are the circles due to which the surface is formed. So, then if this plane cuts, so this is the circle. Okay. So, this surface is formed as a result of family z equals to d. Okay. So, similar thing is happening here. So, these are the characteristic curves. Okay. So, another example. So, the same one I have discussed. So, this is very physically this gives a lot of insight. Psi of x square plus y square z equals to 0 is a surface generated by circumferences parallel to x y plane with center on z axis. Okay. So, this is the surface of revolution. Okay. So, for example, these are the characteristic curves, then this will be our solution. Okay. So, this is the physical interpretation. Okay. So, having discussed first order, okay. So, it will be so this is a simple case where either constant coefficients or if you have variable coefficients, how to solve using Lagrange's method. Of course, the constant coefficients and then even the variable coefficients that we have seen, they are very minimal effort is required. However, in particular cases in order to use Lagrange's method, really we have to spend a lot of time in order to come up with what could be the characteristic curves. Okay. So, it depends on the complexity of the PDE. Okay. So, before we proceed to second order, let us look at some little bit of complicated cases. Okay. So, these can be better ones to solve. Okay. At home. So, consider this. So, from this so we get okay. So, this is possible approaches. So, somebody may try like this, somebody may try like this, okay, or somebody may. So, I am just trying to explain what are the different. So, somebody may try these two to come up with, then this a combination u plus c 1 equals to x plus y square, which we got. So, these two together u is so this is the general solution. Still this is not complex enough, strictly speaking. Okay. Still this is not complex enough. So, there is a slightly different approach using parametric form. So, consider the simplest example that we have considered. So, then for this the characteristic equations, the auxiliary equation. So, now we are introducing this parameter. So, this implies okay. So, this implies so, from this S equals to y minus k 2. So, what is our aim? We get the characteristic curves only when eliminate the parameter S. So, this implies x is this. So, this implies y is Okay. So, this implies k 3 z some k 4. Okay. So, the general solution psi of z so this implies z equals to some other c, let us say some d. Okay. So, these are various ways of solving first order PDE. Okay. So, this is Lagrange's method still, but however, depending on the combinations we try to get the solution. Okay. So, within the framework of Lagrange's, one can attempt the solution using variable coefficients or constant coefficients. Okay. So, but the bottom line is one should understand that the once you write down the auxiliary equations, you get two family of curves, and by eliminating the arbitrary constants we generate the surface. Okay. So, which represents the integral surface. Okay. So, all that I would like to inform you is you must understand that solution of a PDE represents a surface which we call integral surface. Of course, further classification is possible, and then classification of integrals is also very much possible, but since this course is restricted to numerical treatment, we defer those things and we proceed to second order classification, then we proceed to numerical methods of these partial differential equations. Okay. So, in the next lecture we will discuss about second order classification. Until then, bye.